In the previous video of Vant Hoff factor, we have discussed Vant Hoff factor I is equal to the number of ions after dissociation or association divided by the number of ions before dissociation or association. It is also equal to the observed colligative property divided by theoretical colligative property, or it is also equal to the theoretical molar mass over observed molar mass. In the previous video of Vant Hoff factor, I have discussed how these formulas are interrelated to each other. Today we are going to discuss Vant Hoff factor and degree of dissociation. So let's see what is degree of dissociation. Degree of dissociation is the extent to which electrolyte get ionized. It is expressed by alpha. Mathematically, alpha is equal to the number of molecules get ionized over the number of molecules taken. Degree of dissociation is 1 for strong electrolyte as they undergo complete dissociation. For example, if NaCl is there, it dissociates into Na plus ion and Cl negative ion. If there were 100 molecules of NaCl at the beginning, and all 100 molecules undergo dissociation. So alpha for NaCl will be equal to number of molecules get ionized. So here all 100 molecules get ionized, and at the beginning number of molecules taken. So we have taken 100 molecules. So here alpha will be equal to 100 over 100. So here you will get 1. So that's why degree of dissociation is 1 for strong electrolyte that undergo complete dissociation. And degree of dissociation is less than 1 for weak electrolyte because they do not dissociate completely. For example, BaSO4. It dissociates into Ba2 plus ion and SO4 to negative ion. At the beginning, I have taken 100 molecules and only 10 molecules get dissociated. So here I will get 100 minus 10. So for alpha, let's discuss Vant Hoff factor and degree of dissociation in case of complete dissociation. We just have discussed degree of dissociation will be equal to 1 if there is complete dissociation. And Vant Hoff factor will be equal to the number of ions produced after dissociation. Let's try to understand. Alpha is the degree of dissociation and we have the formula alpha is equal to the number of molecules get ionized over the number of molecules taken. For example, if NaCl is there, it dissociates into Na plus ion and Cl negative ion. If at the beginning 100 molecules of NaCl were taken, at all 100 molecules undergo dissociation. So alpha will be equal to number of molecules get ionized. So here all 100 molecules get ionized and at the beginning 100 molecules were taken. So here you will get alpha is equal to 1. And Vant Hoff factor is I. It is equal to the number of ions after dissociation or association over the number of ions before dissociation or association. In case of NaCl, number of ions produced after dissociation, so 1 Na plus and 1 Cl negative ions are produced. So total 2 ions are produced. So here you will get 2 and number of ions before dissociation or association. So there were just NaCl before dissociation. So 2 over 1 is equal to 2. So here Vant Hoff factor I is equal to the number of ions produced after dissociation. As there are 2 ions produced after dissociation, I will be equal to 2. Now come to the Vant Hoff factor and degree of dissociation in case of incomplete dissociation. For incomplete dissociation, degree of dissociation will be less than 1. And Vant Hoff factor will be less than the number of ions produced after dissociation. As we just have discussed, Alpha is equal to the number of molecules get ionized over the number of molecules taken. For example, BaSO4. After dissociation, it gives Ba2 plus ion and SO4 2 negative ion. If at the beginning 100 molecules of BaSO4 were taken and only 10 molecules undergo dissociation, so alpha will be equal to 10 divided by 100. So here you will get 0.1, which is less than 1. That's why the degree of dissociation is less than 1 in case of incomplete dissociation. And now come to the Vant Hoff factor. In case of incomplete dissociation, Vant Hoff factor will be less than the number of ions produced after dissociation. I is equal to the number of ions after dissociation divided by number of ions before dissociation. After dissociation, one Ba2 plus ion and one SO4 2 negative ions are produced, which is equal to 2. Here I will not equal to 2. It will be less than 2 as it undergo incomplete dissociation. Let's establish the relation between degree of dissociation and Vant Hoff factor. Let's take an example of AXBY type of molecule. When it dissociates, it gives X moles of A plus ions and Y moles of B negative ions. Initially, there were just 1 mole of AXBY molecule and there were 0 moles of cations and anions. At time t, when alpha moles of AB molecule get dissociated, so 1 minus alpha moles of AXBY molecule will remain and X alpha moles of A cation will produce and Y alpha moles of B anion will produce. For Vant Hoff factor, we have formula I is equal to number of moles after dissociation over the number of moles before dissociation. So here number of moles after dissociation will be equal to 1 minus alpha plus X alpha plus Y alpha. These are the number of moles after dissociation, and before dissociation there were just 1 mole of AXBY molecule. So here you will get I is equal to 1 minus alpha plus X alpha plus Y alpha. When you take out alpha common, so here you will get 1 plus alpha under the bracket minus 1 plus X plus Y. Let X and Y is equal to n dash. Here X and Y are the number of ions produced after dissociation. Here X and Y number of ions are produced and which is equal to n dash. Now when you substitute the value of X plus Y in this formula, you will get I is equal to 1 plus alpha in bracket minus 1 plus n dash. When you rearrange it, you will get I is equal to 1 plus alpha in bracket n dash minus 1. When you transfer 1 to the other side of the equation, you will get I minus 1 is equal to alpha in bracket n dash minus 1. Now when you transfer n dash minus 1 to the other side of the equation, it will go in the denominator and you will get alpha is equal to I minus 1 over n dash minus 1. And it is the formula that establishes the relation between degree of dissociation and Vant Hoff factor. Let's try to solve some questions based on it. Question 1. An electrolyte AB is 50% ionized in aqueous solution. Calculate the freezing point of 1 molar aqueous solution given Kf for water is equal to 1.86 Kelvin per molal. Let's write down what is given in the question. Electrolyte AB is 50% ionized, means percent alpha is given. Percent dissociation, percent alpha is given 50%. Percent alpha is equal to alpha into 100. So here it is given 50. So it will be equal to alpha into 100. So alpha will be equal to 50 divided by 100. So here you will get 0.5. So alpha will be equal to 0.5. And molality of the solution is given 1 molal. And it is aqueous solution, means solvent is water. Kf for water is given 1.86 Kelvin per molal. And we know the freezing point of water is 273 Kelvin. When AB electrolyte dissociate, it will give A plus ion and B negative ion. And we have the formula delta TF is equal to I into KF into M. To calculate delta TF, first we need to calculate the Vant Hoff factor I. As AB electrolyte is 50% ionized, means there is incomplete dissociation. And in case of incomplete dissociation, I will not be equal to the number of ions produced after dissociation. So here one A plus ion and one B negative ion are produced and it is equal to 2. But in case of incomplete dissociation, I will be less than 2. And to calculate the value of I, we have to use the formula alpha is equal to I minus 1 over N dash minus 1, where N dash is the number of ions produced after dissociation. Here there are 2 ions produced after dissociation. So N dash will be equal to 2. Now let's place the value of alpha, which is 0.5, N dash which is equal to 2, to calculate the value of I. So here you will get the equation 0.5 is equal to I minus 1 divided by 2 minus 1. When you solve it, you will get 0.5 is equal to I minus 1. When you transfer minus 1 to the other side of equation, you will get I is equal to 0.5 plus 1. So I will be equal to 1.5 and it is less than 2. Now we have calculated the value of I. So we can calculate delta TF by using this formula. So we have calculated I is equal to 1.5 and molality of solution is given 1 molal. Kf is already given 1.86 Kelvin per molal. Let's place the value in this formula. So here you will get delta TF will be equal to 1.5, that is the value of I, multiplied by 1.86 Kelvin per molal multiplied by 1 molal. So here molal and per molal will get cancelled out, and when you multiply it, you will get delta TF is equal to 2.79 Kelvin. When you expand this equation, you will get delta TF is equal to TF naught minus TF. TF naught is the freezing point of solvent. Here solution is aqueous solution, that means the solvent used is water. For water, TF naught is equal to 273 Kelvin. So when you place the value of TF naught in this equation, you will get 2.79 Kelvin is equal to 273 Kelvin minus TF. When you rearrange the equation to get TF, you will get TF is equal to 273 minus 2.79 Kelvin. When you subtract it, you will get TF is equal to 270.21 Kelvin, and it is the answer for our question. Now come to the next question. An aqueous solution containing 12.48 grams of barium chloride in 1 kg of water boils at 373.08 Kelvin. Calculate the degree of dissociation of barium chloride. Given Kb for water is equal to 0.52 Kelvin per molal, molar mass of BaCl2 is equal to 208.34 gram per mole. Let's note down what is given in the question. Here barium chloride is the solute and water is the solvent. So mass of solute, that is barium chloride, is given 12.48 grams. Mass of solvent, that is water, is given 1 kg. And the solution boils at 373.08 Kelvin. That is the boiling point of solution. It is TB is equal to 373.08 Kelvin. And Kb for water is given 0.52 Kelvin per molar. Molar mass of BaCl2 is given 208.34 grams per mole. And we know boiling point of water, that is TB naught, is equal to 373 Kelvin. Here we have to calculate degree of dissociation, that is alpha. And for the calculation of alpha, we have formula. Alpha is equal to I minus 1 over N dash minus 1, where N dash is the number of ions produced after dissociation. But here, value of I is also not given. So first we have to calculate the value of I to calculate the value of alpha. For the calculation of Vant Hoff factor I, we have another formula. Delta TB is equal to I Kb into M. Now let's expand this equation. When you expand delta TB, you will get TB minus TB naught. And when you expand molality, you will get W2 over M2 into W1, where W2 is the mass of solute. It is given 12.48 grams. M2 is the molar mass of barium chloride. It is equal to 208.34 grams per mole. W1 is the mass of solvent, that is 1 kg. Kb for water is already given 0.52 Kelvin per molar. TB naught, we know it is 373 Kelvin, and TB for solution is given 373.08 Kelvin. So let's place all the values to calculate the value of I. So when you place all the values, you will get 373.08 Kelvin minus 373.0 Kelvin is equal to I multiplied by 0.52 Kelvin per molal, which is the Kb for water given in the question. W2 is 12.48 grams divided by M2, that is 208.34 grams per mole multiplied by 1 kg, that is the mass of solvent. Here gram and gram will get cancelled out. When you subtract these values and when you convert 12.48 and 208.34 into scientific notation, you will get 0.08 Kelvin is equal to I into 0.52 Kelvin. Molal can also be written as mole per kg because it is the unit of molality. Either you can write molal or you can write mole per kg. So here when you replace molal with mole per kg, here we have converted 12.48 into scientific notation up to 2 digits. So here you will get 1.24 into 10 mole because this per mole will go in the numerator, and in the denominator you will get 2.08 into 10 raised to 2 kg. Now when you apply minus 1 to the bracket, you will get 0.08 Kelvin is equal to I into 0.52 Kelvin. Kg will go in the numerator and mole will go in the denominator. So here you will get kg per mole. So here mole and this mole will get cancelled out. Kg and kg will get cancelled out. Now let's convert 0.08 and 0.52 into scientific notation. So here you will get 8 into 10 raised to minus 2 is equal to I into 5.2 into 10 raised to minus 1 multiplied by 1.24 into 10 divided by 2.08 into 10 raised to 2. 2.08 can be taken approximately is equal to 2, and when you divide 5.2 by 2, you will get 2.6. 10 and 10 raised to minus 1 will get cancelled out. So here you will get 8 into 10 raised to minus 2 is equal to I into 2.6 multiplied by 1.24 divided by 10 raised to 2. When you multiply 1.24 and 2.6, you will get 3.22. And 10 raised to 2, which is in the denominator, can also be written in the numerator in the form of 10 raised to minus 2. Now rearrange this equation to get the value of I. So here you will get I is equal to 8 into 10 raised to minus 2 over 3.22 into 10 raised to minus 2. 10 raised to minus 2 and 10 raised to minus 2 will get cancelled out. When you divide 8 by approximately 3, you will get 2.6, and it is the value of I that we just have calculated. By using the value of I, you can calculate degree of dissociation by using formula alpha is equal to I minus 1 over n dash minus 1, where n dash is the number of ions produced after dissociation. So let's calculate the number of ions produced after dissociation of barium chloride. When barium chloride dissociates, it dissociates into Ba2 plus ion and 2Cl negative ion. So one Ba2 plus ion and 2Cl negative ion, they are equal to 3. So the n dash value will be equal to 3. Now place the values of I and n dash in the above equation. So here you will get alpha is equal to 2.6 minus 1 divided by 3 minus 1. When you solve it, you will get 1.6 divided by 2. So here you will get alpha is equal to 0.8. That is the answer for our question. Now come to the degree of association or dimerization. For example, A type of molecule is there and it dimerized to form A2. At the beginning, there was 1 mole of A type of molecule. And after association at time t, 1 minus alpha moles of A will remain and alpha by 2 moles of A2 are produced. We have formula for the Vant Hoff factor, I. It is equal to the number of moles after association over the number of moles before association. So after association, 1 minus alpha mole and alpha by 2 moles are produced. And before association, just 1 mole of A molecule is there. So I will be equal to 1 minus alpha plus alpha by 2 over 1. So when we rewrite it, you will get I is equal to 1 minus alpha plus alpha by 2. Now transfer 1 to the other side of the equation. So here you will get I minus 1 is equal to minus alpha plus alpha by 2. Now multiply both sides by minus. So when we multiply both sides by minus, you will get 1 minus I is equal to alpha minus alpha by 2. When you subtract alpha by 2 from alpha, you will get alpha by 2. So here you will get 1 minus I is equal to alpha by 2. Now rearrange this equation to get the value of alpha. So here you will get alpha is equal to 2 multiplied by 1 minus I. And this is the formula for dimerization. Now let's try to solve one question based on it. Phenol dimerises in benzene having Vant Hoff factor 0.54. Calculate its degree of association and percent association. So here it is given phenol dimerises, means if 2 moles of phenol are there, it dimerizes to form phenol dimer. Vant Hoff factor I is given 0.5. And for the calculation of degree of association, that is alpha, we have formula. Alpha is equal to 2 into 1 minus I. Value of I is given 0.54. So let's place the value of I in this equation and you will get alpha is equal to 2 multiplied by 1 minus 0.54. When you subtract 0.54 from 1, you will get 0.46. And when you multiply it by 2, you will get alpha is equal to 0.92. So here we have calculated the degree of association alpha. Now we have to calculate percentage association. For percentage association, we have formula percent alpha is equal to alpha into 100. We just have calculated the value of alpha, that is 0.92. So let's place the value of alpha in this equation. So here you will get 0.92 into 100. When you solve it, you will get percent alpha is equal to 92%, and this is the answer for your question. Now come to the next question. Determine the osmotic pressure of a solution prepared by dissolving 25 milligrams of K2SO4 in 2 liters of water at 25 degrees centigrade, assuming that it is completely dissociated. Given molar mass of K2SO4 is equal to 174 grams per mole. Let's note down what is given in the question. Here K2SO4 is a solute and water is a solvent. Mass of K2SO4 solute is given 25 milligrams. Molar mass of K2SO4 is given 174 grams per mole. Volume of solvent water is given 2 liter at 25 degrees centigrade. Here we have to assume complete dissociation. So let's calculate I value for K2SO4. When K2SO4 dissociates, it dissociates into 2 K plus ion and 1 SO4 2 negative ion. So at the beginning, there was 1 mole of K2SO4 and 0 moles of K plus and SO4 2 negative ions. After complete dissociation, there will be 0 moles of K2SO4 and 2 moles of K plus ions are produced and 1 mole SO4 2 negative ions are produced. Let's calculate the Vant Hoff factor I by using formula number of moles after dissociation over the number of moles before dissociation. So after dissociation 1 plus 2 is equal to 3 moles are produced and before dissociation there was just 1 mole of K2SO4. So I will be equal to 3 by 1 and it is equal to 3. So we just have calculated the value of I, that is Vant Hoff factor. Here we have to calculate osmotic pressure. For osmotic pressure calculation we have formula pi is equal to I N over V R into T, where pi is the osmotic pressure, N is the number of moles of solute, that is K2SO4, V is the volume of solvent, that is water, R is the gas constant and its value is 0.0821 liter atmosphere per Kelvin per mole. T is the temperature in Kelvin. Here temperature is given 25 degrees centigrade. To convert degree centigrade into Kelvin, you have to add 273. So here you will get 298 Kelvin. Here number of moles of solute are not given in the question, but we can calculate it by using formula. Moles of solute is equal to given mass over molar mass. Here given mass is 25 milligram and molar mass is 174 grams per mole. It is in gram and it is in milligram. So first you have to convert milligrams into gram. We know 1 milligram is equal to 10 raised to minus 3 grams. So 25 milligram will be equal to 25 into 10 raised to minus 3 grams. Now let's calculate the number of moles of solute. So here you will get 25 into 10 raised to minus 3 grams over 174 grams per mole. For osmotic pressure calculation, we have formula pi is equal to I n over V R into T. We just have calculated the number of moles n is equal to 25 into 10 raised to minus 3 grams over 174 grams per mole. Now place the value of n in the above equation. So here you will get pi is equal to 3, that is the value of I, multiplied by value of n is 25 into 10 raised to minus 3 grams over 174 grams per mole, multiplied by 2 liters, that is the volume, multiply by the value of R, that is 0.0821 liter atmosphere per Kelvin per mole, multiply by temperature, that is 298 Kelvin. Now this gram and gram will get cancelled out. Per mole and per mole will get cancelled out. This liter and liter will get cancelled out. Per Kelvin and Kelvin will get cancelled out. Now convert 0.0821 into scientific notation. So here you will get pi is equal to 3 into 25 into 10 raised to minus 3 over 174 into 2 multiply by 8.2 into 10 raised to minus 2 atmosphere into 298. So let's simplify this equation. Here we can cancel out 174 by 3. So here you will get 58. When you cancel out 298 by 2, you will get 149 and 2 ones are 2. And when you multiply 10 raised to minus 3 and 10 raised to minus 2, you will get 10 raised to minus 5. So here you will get 25 into 10 raised to minus 5 multiply by 8.2 into 149 atmosphere divided by 58. Now when you divide 58 and here approximately you will get 2.5. Here you will get 25 into 10 raised to minus 5 multiply by 8.2 into 2.5 atmosphere. When you multiply 25 and 2.5, you will get 62.5, and when you multiply 62.5 by 8.2, you will get 512 into 10 raised to minus 5 atmosphere. When you convert it into scientific notation, you will get 5.1 into 10 raised to minus 3 atmosphere. And it is the answer for your question.